Hi everyone, welcome to Faster ML Model Training and Experimentation with Vertex AI. I'm Nikita, I'm a Google Cloud Developer Advocate, and today I'm going to show you how to use Vertex AI for hyperparameter tuning and distributed training. Vertex AI is Google Cloud's managed machine learning platform, and by the end of this session, you'll know how to use the Vertex AI managed training service to train a TensorFlow model using distributed training, and how to launch multiple trials of your training code for automated hyperparameter tuning. Now, while we'll be using TensorFlow for today's example, the concepts are applicable to other machine learning frameworks as well. So you could also run hyperparameter tuning on Vertex AI with PyTorch, XGBoost, etc. Now, before we get into how to do this, I want to spend a minute talking about why we want to do this in the first place. The values you select for your model's hyperparameters can make all the difference. If you're only trying to tune a handful of hyperparameters, you might be able to run experiments manually. However, with deep learning models where you're often juggling hyperparameters for the architecture, the optimizer, the batch size, the learning rate, automating these experiments at scale quickly becomes a necessity. And it's not just about tracking the results from all of these experiments. You also want a way to efficiently search the space of possible values so you don't waste as much time trying out combinations that yield low accuracy scores. But training a model once takes long enough. So having to run multiple trials of your training code, each with different values, can be very time consuming. So we're going to leverage Vertex AI for two key things. The first is a serverless hyperparameter tuning service, which will help us to both track the values from our trials and intelligently select the values to try out. The second is a multi-GPU setup to make our model train faster, because faster model training makes for faster iteration to reach your modeling goals. If you'd like to follow along, all of the steps are documented in this code lab, so feel free to follow along or just watch and then refer to the lab after the session. Let's jump in. If you open up the code lab link, you'll see something that looks like this. And we can click over to section 2, which is the intro to Vertex AI. So as I mentioned earlier, Vertex AI is Google Cloud's managed machine learning platform. There are a lot of different products, and you can see them down here in this diagram. And you can use these products together or with other GCP or open source tools. And today we'll just be focusing on two of these products, Training and Workbench. Training is the serverless training product within Vertex, and Workbench is the managed Jupyter Lab solution within Vertex. So we'll click next, and section 3 just provides a little bit of information on the actual use case for today. So we'll be using hyperparameter tuning to help us to discover optimal parameters for an image classification model that will train on the horses or humans dataset. So we can click on this data set. This is pulled from TensorFlow datasets, and we can take a look. And as you might imagine, as the name implies, this data set has images of horses and humans. So we'll be building an image classification model that tries to identify whether an image is of a horse or a human. So there are kind of two key concepts we'll be working with today. The first is hyperparameter tuning. And the way that hyperparameter tuning works in Vertex AI is that Vertex AI will run multiple trials of the training application using values for our hyperparameters set within limits that we specify. And Vertex AI will keep track of the results of each of these trials and make adjustments for subsequent trials. So I think the easiest way to understand this is just to take a look at the end state. So we can click over here, and this is the Google Cloud Console, and this is what we'll be kind of working up to by the end of this code lab. But you can see down here the accuracy scores for each of our trials. So I'm going to go ahead and sort this. And these are all of the different trials that we ran of our hyperparameter tuning job. And on each trial, we tried out different values for the learning rate, the momentum, and the number of units in the last hidden layer. So these trials were run, and each time Vertex AI recorded the accuracy metric, and we sorted these, and as a result, we can see that the trial that had the highest accuracy value was this trial ID number 5. And so that means that these are the values we would want to set for our learning rate, the momentum, and the number of units. So this gives you just a little picture of what we'll be working up to. So back in the lab, the second component that is important to this hyperparameter and distributed training job is using the TF-distribute module. So if you have a single GPU, TensorFlow will use this GPU to speed up model training without any extra work on your part. But if you want to get an additional boost by using multiple GPUs, you'll need to use a strategy from the TF-distribute module. This is a module that helps you to run computation across multiple devices. And today we'll be using the mirrored strategy, which is the simplest strategy to get started with. It allows you to train a model across multiple GPUs within a single machine. So there is a little bit of detail added in this lab here to explain kind of what mirrored strategy is doing. But honestly, you don't really need to know the details in order to use it in your code and get the benefit. So I'm going to skip over that, but I did link to a video that I recorded that goes a lot deeper into how distributed training works in TensorFlow and a little bit of the theory. So if you're curious, feel free to check out this video linked here. Now, today we're going to use both distributed training and hyperparameter tuning, but note that with Vertex AI, you can use a hyperparameter tuning job without distributed training, and you can also do distributed training without hyperparameter tuning and just train a model with multiple devices. But today we're going to see how to use both. So with that, we are ready to jump into the lab. So I'm in the Google Cloud Console, and I'm in a project where I have billing enabled. So in order to run this, you'll need to make sure that your project does have a billing account associated with it. And I'm currently in the Vertex AI section. I got there by clicking on the navigation menu, and I've actually pinned Vertex AI to the top here. But if you don't have it pinned, you'll just need to scroll all the way down to the artificial intelligence section right here, and you can select Vertex AI. So before you get started, you will need to set up a couple different APIs. You'll need to make sure that you have the container registry API enabled, as well as the compute engine API enabled. And I've gone ahead and done that already just because it takes a couple minutes. But if you need to still do that, be sure to check out step 4 in the code lab, which will show you how to enable both of these APIs. Additionally, if you've never used Vertex AI in your project before, you will be prompted here on this home page to enable the API. So be sure to click that button and make sure it's enabled. And once that's done, you can click over here on the left to where it says Workbench. And Workbench is GCP's managed notebook solution. So we'll click on Managed Notebooks up here at the top, and you can see a couple of existing notebooks that I already have. If you have not used Workbench in your project before, you will be prompted here to enable the Notebooks API as well. So just make sure that you do that. So the next step is to create a new notebook. We'll click up here where it says New Notebook. And the first thing we'll do is give our notebook a name. And then under Advanced Settings, we can set the idle shutdown time to 60 minutes. So this is just how long the notebook will run before it'll shut down due to inactivity. This is really important just because if you're like me and you forget to shut down your notebook when you're done using it, you won't be charged. And that's great. This just means it's going to shut the notebook down when you're not using it anymore. And so I've just set this to 60 minutes. The next thing you'll want to do is click this Enable Terminal option, and then we can select Create. And this will take about a minute or so to be created, but once this instance has been provisioned, we will see the Open Jupyter Lab text turn blue, and we'll be able to open up our instance and authenticate. Once the text turns blue, you can select Open Jupyter Lab, and you will need to authenticate the very first time that you use the instance. So you can just follow the steps in the UI to get the authentication code. Paste the code, select Authenticate, and we will be in our managed Jupyter Lab instance. So that completes the setup, and now we can get into preparing our training code. So from the launcher menu, I will select on terminal. And this will open up a new terminal instance. And from the lab, we can copy and paste the following commands, which will create a directory called Vertex Code Lab, and then we can cd into that directory, and you'll see that directory show up right over here on the left. The next commands we'll want to run is to make a directory called trainer within that Code Lab directory, and then within the trainer directory, we'll create a file called task.py. So let's take a look. We've got Vertex Code Lab. Within that, we've got this trainer directory. And within that, we've got this file called task.py. So I'm going to open up this task.py file, and this is where we will paste in all of our training code. And this code will contain all of the important steps we need to download the data, pre-process the data, create the model, and train the model. But note that for a more production application, a more realistic application, you'll likely have multiple files within this trainer directory and not just a single file. You'll probably have, a data.py file, which handles all of the data pre-processing. Maybe a model.py file where you create the actual model, some utils to have any helper functions and, import those within your main training task.py file. But for this simple example, I've just included one Python script under the trainer directory that has all of the code we'll need to run a training job. So I'm going to copy and paste in the code from the Code Lab. Okay, so here we have the code, and let's quickly walk through what's going on in this file. So at the top here, we start just by importing the libraries that we need, and then we set a couple of variables. This function called getArgs is what is going to use argparse to parse our command line arguments, and this is where we will include all of the hyperparameters that we want to tune. I'll dive a little bit deeper into this in just a minute when we talk about how to use the hyperparameter tuning service. This next function, preprocess data, just preprocesses our data by resizing it and also scaling it. And then we have a create dataset function, which is going to load in the data from TensorFlow datasets and then create a training dataset and a validation dataset. So that's what it returns. These datasets have been preprocessed, they've been shuffled, and they've been batched. The create model function will define and compile our model. And this is using the Keras functional API to do so. If you're not very familiar with TensorFlow and Keras, don't worry too much about it. This function is really just here to create the model, and whatever framework you're using, just think about that in context of how you would create a model in that particular framework. Now, the main function is, of course, where most of the stuff is happening. So the first thing we do here is we get our args, and we then create our distribution strategy. So again, there are kind of two high-level concepts we're working with here: distributed training and hyperparameter tuning. So in order to do distributed training, the first thing you need to do is define our distribution strategy. And as I mentioned earlier, we are using the TensorFlow mirrored strategy. So we define that right over here. The next step is to scale our batch size by the number of GPUs that we have. So that's what's happening in this line right over here. Instead of setting the number of GPUs to 2 and just hard coding it right here, I went ahead and used this numReplicas in sync method, which will just return the number of GPUs that we have on our machine. So that's going to be 2 when we launch our training job, because we're going to make use of 2 GPUs, but this just saves us from having to hard code that number in here. And the reason we scale this batch size is now because we have 2 GPUs or we have multiple GPUs, we want to make sure that we're using every GPU to its maximum potential. So scaling up the batch size is a best practice when you use the mirrored strategy from the TF Distribute module. And again, if you'd like to learn a little bit more about why that is the case, be sure to check out the video, which I have linked in the training code section of the Code Lab as well. And then the last step you'll need for TF distribute is to wrap the creation of your model variables within the scope of the strategy. So that's what's happening in line 89. We call with strategy.scope, and then we call the create model function. And again, the create model function is what creates the model and also compiles it. So that's where all of our model variables get created. And that's all you need to do in order to make use of distributed training. This now means that when our model training kicks off, it will be able to use multiple GPUs in order to train faster. So the next important things we need to do are make sure that our code is prepared to do hyperparameter training with Vertex AI. So the first thing you'll want to do is all the way up at the top, where we import the Hypertune library. So this library here basically helps us to report the metrics that we care about to Vertex AI. And recall earlier, I showed you kind of what that end state looks like, where we have multiple training trials and we were recording the accuracy of those different trials. This Hypertune library is what's going to help us do that. So after you've imported the Hypertune library, the next thing you need to do is create this getArgs function, and you'll use argparse to define all of the hyperparameters that you want to tune. So in this case, we have chosen to tune the learning rate, the momentum, and the number of units in the last hidden layer. And these are just 3 hyperparameters that I chose to tune, but feel free to experiment with others or, add more, change these out, whatever you're curious to experiment with. Something to note is that you can call these hyperparameters whatever you like. I chose, learning rate, momentum, num units. These string values are up to you to decide. You just need to make sure that you are consistent everywhere. When you launch the job, you'll want to refer back to these strings as well. So just make sure you're consistent, but otherwise you can call them whatever you like. Now, the next thing we'll need to do in order to use the hyperparameter tuning service is to define our metric. So that's what's happening over here in line 96. It's important that we have a metric that we are tracking because we want to know how effective each trial of our hyperparameter tuning job, how effective each trial was, right? If we just were to run multiple trials but not be tracking a metric, we would have no idea which trial was the most performant. So in this case, I've decided that validation accuracy is the metric that I want to track, but it might be different for, of course, a regression problem or maybe a problem with class imbalance. Whatever metric it is that you think is relevant to your problem, you'll want to define that. And I've defined that as this HP metric right here. Now, this might look a little strange, but this is just something that's particular to Keras. When you use model.fit in Keras, as we have here, it will return this history object. And the history.history attribute is a record of the training loss values and metric values at successive epochs. So when we compiled the model, we passed in this accuracy metric right here. And that just means that our history.history attribute is going to keep a record of both the loss as well as the accuracy for our training and our validation data sets on each epoch. So here I'm just extracting out the validation accuracy key, and I'm pulling the last value from that list because we want the last epoch's accuracy measure. If you're using a different framework such as scikit-learn, I think scikit-learn has that accuracy score function. So that's really what you would use here. This is just your calculation of the metric that you care about. And once you have defined and calculated that metric, and again, in this case, we're interested in the validation accuracy, we will go ahead and create an instance of Hypertune using this Hypertune library. And then we will pass in a tag for our metric. We're going to call it accuracy. And then we will also pass in the actual metric value, which we defined as HP metric. So what this means is that each time our training code is run, we'll have this model.fit, it'll train the model. And then after the model has been trained, we're capturing what the validation accuracy looked like on the last epoch, and we're reporting that to Vertex AI so that each time we run one of these training trials, we're able to see what the validation accuracy was, and that will help us determine which trial performed the best. With that, we are ready to go ahead and containerize our code. So I'm going to jump back over to the terminal. And from the root of our Vertex Code Lab directory, I will create a Docker file. So we can see that Docker file right over here. And I'm going to paste in the following commands. And what this file is doing here is it's using as the base image over here on line 1, the deep learning container TensorFlow Enterprise 2.7 GPU Docker image. These deep learning containers on Google Cloud come with many common machine learning and data science frameworks pre-installed. And then after downloading that image, we are going to pip install the CloudML Hypertune library. This is the library Hypertune that we import in our script. So you just need to make sure that you install this library if you are using a base image that doesn't already come with this library pre-installed. And then in line 9, we're copying over all this training code to our Docker image. And then in line 12, we will set up the entry point to invoke our trainer. And all this means is that it's going to run our task.py file, which is the file where we had all of our training code. So back in the terminal, we can now go ahead and build and push the container. So the first thing you'll need to do is define a variable for your project ID. Now, I happen to know what my project ID is. However, if you do not know, there is a handy command that's listed in the instructions in the code lab. The next thing we'll want to do is define a variable with the URI of the container image in Google Container Registry, and this is where we will push our image. Container Registry is the place in Google Cloud where you can store any of your Docker images. The next command we'll run is this gcloud auth configure Docker, which will just help us to configure usage of Docker. And then we can go ahead and build our image. And this will take a few minutes, probably about 5 or so minutes, the very first time that you do this. It's going to work a little bit faster for me because I have done this before, but note that the first time you do run this command, it will take a little bit of time. Okay, our image has been built, and now the next step is to push this image to Container Registry. So we'll call Docker push. And again, this will take a little bit of time the very first time you do it. I've done this before, so it was pretty fast. All right, so the last step before we go ahead and launch the hyperparameter tuning job is to create a cloud storage bucket. We will just need a staging bucket for when we launch our training job. So we can go ahead and create our bucket. So I've chosen to call the bucket the name of my project ID -hbtune-bucket. Buckets need to be unique. So this is just an easy way to make sure we create a unique bucket. And you can create the bucket with the following command. I'm not going to execute this command because I've already created this bucket, but if you are creating a new bucket, this command will help you do that. And with that, we are ready to head over to step 7 and launch our hyperparameter tuning job. So the next thing we'll do is go back and open the launcher again one more time, and I will create a TensorFlow 2 notebook. And in this notebook, the first thing we need to do is import the Vertex AI Python SDK. So we can import this SDK. And then we will need to define a couple of different specs. The first spec that we'll define is called the worker pool specs, and this specifies the machine type and the Docker image for our training job. So here we're specifying an N1 standard 4 machine type. We're specifying an NVIDIA Tesla V100 as our accelerator, and we're going to use 2 accelerators. And again, this is so that we have 2 GPUs so that we can do distributed training. Feel free to try out different machine types, different accelerator types, use more or fewer accelerators. The more accelerators you use, of course, the more expensive it will be, but feel free to experiment here however you like. And the only thing you'll need to change is in this image URI, you'll need to add in your own project ID. So there we have our worker pool spec. The next step is to define the parameter spec, and this is a dictionary specifying the parameters that we want to optimize. So in this dictionary, the keys are going to be the strings that we assign to the command line argument for each hyperparameter that we wanted to tune. So recall in our getArgs function earlier, we defined these arguments, learning rate, momentum, and num units. And we're just making sure we use the same strings so that we're consistent. And the value is going to be a parameter specification. And you can check out the Vertex AI Python SDK docs to learn a little bit more about these different specs. But at a high level, hyperparameters can be of type double, integer, categorical, or discrete. If you select the types double or integer, you'll need to provide a minimum and maximum value as well as a scale. I linked in the Code Lab a video that helps you understand a little bit more about how to pick the best scale in case you're curious. And if you select categorical or discrete, you will need to provide the actual values. So in this example, learning rate and momentum are both going to be doubles, and I've provided a minimum and maximum value for each of them. And I've set the learning rate scale to be log and the scale for momentum to be linear. And the number of units is going to just be discrete. So I went ahead and set all of the values. You can see them right here, 64, 128, and 512. And that just means one of these values will get picked. And the scale is, of course, none because we just are picking from a discrete list. So we can execute the cell. And the last step is to define the metric spec. So this is the last spec, and this is the metric that we want to optimize. Again, we were optimizing the validation accuracy, and we called that accuracy. That was the string that we defined earlier as the hyperparameter metric tag that we set in our training application code. And the value here is going to be the optimization goal of that metric, and that can either be maximize or minimize. Of course, we want to maximize accuracy, but you might have use cases where you're tracking a metric that you want to minimize, maybe its loss. But in this case, we want to maximize this metric. That's defined all of the specs that we need. The next step is to define the custom job. This is the common spec that will be used to run the job on each of the hyperparameter tuning trials. So that means that when the hyperparameter tuning job kicks off, multiple custom jobs will be run. This is taking in the worker pool spec, which we defined earlier, where we specified our machine as well as the Docker image that has the training code. So you'll need to make sure that you update your bucket here and that you put in the bucket that we defined earlier. This just needs to be some staging bucket in your project. So we'll define that here. And then we can execute this cell. The next step is to create and run our hyperparameter tuning job. So this hyperparameter tuning job will pass in the custom job that we defined earlier. We'll also pass in the metric spec and the parameter spec. And then these last three arguments are specific to running hyperparameter tuning jobs. The first is the max trial count. You'll need to put an upper bound on the number of trials that the service will run. And generally, more trials will lead to better results, but you will reach a point of diminishing returns after which additional trials have little or no effect on the metric that you're trying to optimize. So generally, a best practice is to start with a smaller number of trials, get a sense for how impactful your chosen hyperparameters are, and then scale up as needed. The second argument is the parallel trial count. And if you choose to use parallel trials, the service will provision multiple training processing clusters. Increasing the number of parallel trials will reduce the amount of time overall that the hyperparameter tuning job takes to run. However, the downside is that it can reduce the effectiveness of the job overall. And that's because the default tuning strategy will use results of previous trials to inform the assignments of values in subsequent trials. So we're defining that tuning strategy here in the search algorithm argument, which we've set to none. And that's because by default, this default option will apply a Bayesian optimization algorithm to search the space of possible hyperparameter values. This is the recommended algorithm. And I have linked to a blog in the Code Lab, which has a little bit more information on the mathematics of how this works. If you're curious, it's really interesting, so definitely worth checking out. So with that, we will launch our hyperparameter tuning job. So now that our job has kicked off, we can head back over to the Google Cloud Console, and we can head to the training tab right here. And we can go to hyperparameter tuning jobs, and we can see that the job we just kicked off is currently running. So we can click on this job, and we won't see a whole lot yet because nothing's happened yet, but we can see kind of the start time, when it was created, how long it's been running for. We can check out the specs that we defined all here. These are all the specs that we defined in our notebook. And then eventually when the trials are run, we'll be able to see the results down here. So this is going to take about 30 or so minutes. So I'm going to hop back over and we'll just take a look at a job that I've run in the past that has already completed. And this will be the same end result. And this is what I showed at the beginning. So let's go ahead and see all of the trials at once. And we can go ahead and sort these by accuracy. So what happened behind the scenes is that our training code that we defined in that task.py file, it was executed 6 different times because we chose to run 6 different trials. Each of those trials tried a different learning rate, momentum, and number of units. And you can see the combinations that were selected right over here. And on the 10th epoch, which was the final epoch of our training job, we can see the validation accuracy score that was reported. We, of course, want the trial that led to the highest accuracy score. So that's trial ID 5, and it had the following learning rate, momentum, and number of units. So if 0.82 was a good enough accuracy score for our particular use case, we could go ahead and set these hyperparameters to the values here. If we wanted to aim for higher accuracy, we could go ahead and run even more trials, since 6 is a pretty low number, and see if we can do even better on this data set. And one other last note is that you can actually do all of this through the UI. So if we click back over to training, you can click on this create button here, and you can actually create a training job. And under step 4 here, you'll have the option to set your hyperparameters. So if you prefer to do this through a UI instead of doing this via the SDK, that is also an option. So that concludes the workshop for today. We saw how to use Vertex AI for hyperparameter tuning and distributed training. We used a Vertex AI managed Workbench instance, as well as the Vertex AI Python SDK to help us to launch and configure this hyperparameter tuning job. I hope this gives you an idea of how you can use Vertex AI to help you with model training and faster experimentation for your own machine learning use cases. And if you build something cool with Vertex AI and with notebooks, definitely let me know. Thanks so much for watching, and I hope you get a chance to run through the code lab yourself.